All right, let's talk about Cilium. It's a technology that is totally rewriting the rules for cloud-native networking. Today, we're going to look at two of its superpowers, you could say, by diving into a couple of real-world cases that show just how it's solving some massive headaches, both in terms of speed and simplicity. First up, we've got a high-stakes performance battle that pushed one technology right to its breaking point.
You know, this is the kind of question that keeps engineers up at night. You've spent all this time optimizing your code, you've scaled up your servers, but what if the very network connecting everything together is what's holding you back? It's a nightmare scenario, and it perfectly sets the stage for the first challenge we're going to look at.
So our first story kicks off in an on-premise data center that's just getting hammered with traffic. And the big problem is high-performance load balancing. Now, for years, the undisputed champ for handling this in the Linux world has been a tool called IPVS. But as you're about to see, even champions get old, and it's starting to buckle under the pressure of modern workloads.
Yeah, this is the classic setup pretty much everyone knows. Traffic flows in from the internet, IPVS acts as the traffic cop, telling all the packets which backend service to go to. It's a system that has worked, and worked well, for a very long time. But what happens when rush hour turns into a full-blown traffic apocalypse?
And this is where the fun begins. A team decided, you know what? Let's put the old guard, IPVS, in a direct head-to-head battle with the new challenger, Cilium. And Cilium isn't coming to this fight alone. It's powered by some seriously cool modern tech in the Linux kernel called eBPF and XDP. Let's see who comes out on top.
So, let's meet our contenders. In this corner, we've got IPVS, the tried-and-true veteran. And in the other corner, the challenger, Cilium. Now, Cilium's secret weapon is something called XDP, which lets it process network packets right when they arrive at the network card, before they get bogged down in the rest of the system. Think of it like a bouncer who can direct traffic at the front door instead of letting everyone get crowded in the main hallway. The stage is set.
Okay, round one, 1 million packets per second. Now that's a lot of traffic, but it shouldn't be a knockout blow. But whoa, look at that. IPVS is already sweating. One of its CPU cores is completely pegged, and even worse, legitimate users, their connections are starting to fail. Oof, not a great look for the incumbent. And there it is. At 3 million packets per second, it is lights out for IPVS. It hits a complete brick wall, the CPU is screaming at 100%, and the system just collapses. We're talking nearly every single real request getting dropped. This isn't just struggling, it's a catastrophic failure.
So, what about Cilium? Well, at 3 million packets, it was basically yawning. So the team just kept cranking the dial up, all the way to 10 million packets per second. The result? Cilium handled it with so little CPU usage, the numbers were barely worth looking at. And every single client request sailed right through without a problem. I mean, the difference is just staggering.
This chart just says it all, doesn't it? IPVS tapped out at 3 million packets per second. Cilium, it just kept on going until it hit almost 15 million. And get this, the only reason it stopped there was because the physical network card itself couldn't handle any more data. The software was ready for more. That's just an unbelievable leap in performance.
Okay, so lab tests are great. But what does this mean in the real world, right? What happens when you drop this into a live production environment with actual user traffic? Well, that's exactly what the team did next.
And when they saw the production results, the lead engineer on the project, Andrei Blazik, said this. The numbers were so good, they literally thought their monitoring was broken. You know that feeling when a new piece of tech is so much better it almost feels like magic? Yeah, it was one of those moments.
And here is exactly why they were so shocked. To handle their normal live traffic, about 800,000 packets a second, the old IPVS setup needed a grand total of 36 CPU cores. 36! The new single Cilium node, handling that exact same traffic load, it used, wait for it, half a core. Let me just say that again so it sinks in. 36 cores, down to half a core.
So what does that really mean? It means just by swapping out a fraction of their old setup, they instantly freed up 36 CPU cores. That's real money. That's hardware you don't have to buy, power you don't have to pay for, and space in the rack you get back. That is the bottom line impact. But you know, raw speed is only half the story.
All right, let's switch gears completely. For our second challenge, we're not talking about speed anymore. We're talking about something that can be just as painful: complexity.
especially when you're trying to get the new world of Kubernetes to play nice with your, let's call it, classic on-premise infrastructure.
This is a problem so many people run into. You've got this great service running inside Kubernetes, but you've also got an older physical server or a VM sitting right there on the same local network. How in the world does that old server find the new service? The textbook answer usually involves something called BGP, which is a super complex routing protocol. And honestly, for most environments, that's like using a sledgehammer to crack a nut.
So to really get the solution here, let's do a super quick networking 101. Think of your local network, that's layer 2, as your street. Every house has a specific address, like 123 Main Street. That's a MAC address. Now layer 3 is like the global postal service, using zip codes to get mail anywhere in the country. Those are your IP addresses. The challenge is, how do you tell a house on your local street how to find a zip code that doesn't actually belong to any single house?
So instead of forcing every device on the network to learn a whole complicated new routing system, Cilium does something much, much smarter. It uses a basic language that every single device on that local network already speaks. It's simple, it's elegant, and it's kind of brilliant.
Here's how it works. The non-Kubernetes client basically just shouts out to the whole local network, "Hey, I'm looking for this IP address. Does anyone know where it is?" This is called an ARP request. And one of the Cilium nodes in the Kubernetes cluster just raises its hand and says, "Yep, that's me. Send the traffic right over here to my physical address." And boom, done. The client knows exactly where to go. No BGP, no complex configs, no mess. It just works.
Okay, but the obvious question is, what happens if that one node that's answering the call goes down? This is the really cool part. Let's say node 2, the one handling the announcements, suddenly gets unplugged. The cluster notices in about 3 seconds, and instantly another node, worker node 1 in this case, just picks up the job. It starts answering for that same service IP. For the client, on the other hand, it's just a tiny little hiccup, and then traffic is flowing again. It's not just simple, it's incredibly resilient.
So let's just take a step back and look at what we've seen. We saw Cilium, powered by eBPF, take on two completely different but really difficult problems. One was a raw, brute force performance issue, and the other was a tangled mess of integration complexity. And it solved both of them beautifully.
So, what are the big takeaways? Well, first, you get absolutely blazing speed, more than 10 times the performance of the old way. Second, that performance translates directly into massive savings on hardware and cost. Third, it radically simplifies how you connect Kubernetes to your existing networks. No more BGP headaches. And finally, you get automatic resilience and failover baked right in. It's the whole package.
And that really leaves us with one big final question. If this eBPF technology can completely upend the world of networking, if it can rewrite the rules for performance and simplicity like this, what's next? What other parts of our systems is it going to re-engineer tomorrow? Because what we've seen today, as amazing as it is really just the beginning of that story.
Thanks for joining me.